Hi, thanks for watching the video about section 7.1, confidence intervals for the mean when sigma is known and sample size, which is what this section is about. So two separate topics. First, confidence intervals, and then sample size. Let's say you want to know what is the average weight of all the pink elephants in the world. Now, assume for the sake of the example that there are lots of pink elephants in the world, but you can't track down and weigh every single one of them. If you could get access to every single pink elephant in the whole world and weigh them all, and then take all those weights and add them together and divide by how many there are, that would be the average or mean weight of all the pink elephants in the world. But it's too big a job to go out and get every single last one of them, weigh them all, and then use all of those numbers in your calculation. But let's say you can get yourself a sample of 50 pink elephants. You go out to the vast herds of pink elephants and you somehow randomly select 50 of them. And you weigh those 50 pink elephants, and you take those 50 numbers, you add them all together, divide by 50, and it turns out that the mean weight of those 50 elephants turns out to be 9,650 pounds. So that would be X bar. Remember, X bar is the symbol for a sample mean. So X bar, the sample mean, the mean or average weight of the elephants in your sample is 9,650. Based on that, your best guess for the population mean, mu, that would be the mean weight of all pink elephants in the world. If you just had to pick a number, the best number to pick would be 9,650 pounds. Now, because of sampling error, because of the fact that your sample doesn't include all the pink elephants in the world, just some of them, hopefully a representative sample, but it's not exactly the same as if you could measure all the pink elephants in the whole world. So the population mean is probably at least a little bit different from what you got from your sample. Probably a little bit different, but that's the best you can do if you're going to pick a number and say, well, that number is my best guess for the population mean. It's the best point estimate. So a point estimate is a single number, just one number that does as good a job as you can of estimating something, in this case, the population mean, that you don't have an exact true value for. So it would be correct, but kind of vague, to say something like, I think mu, that is the average weight of all the pink elephants in the world, is somewhere around 9,650 pounds. Now, a statistician would like to be a little more precise than just somewhere around 9,650 pounds. So a statistician might be able to do some calculations and say something like, I'm 99% sure that the true population mean weight is within 300 pounds of 9,650. In other words, they're 99% confident that it's 9,650 plus or minus 300 pounds, which would put it somewhere between 9,350 and 9,950. Or they might say, I'm 90% sure that the true population mean is within 40 pounds of 9,650. So 9,650 plus or minus 40 pounds puts you somewhere between 9,610 and 9,690. Notice we narrowed it down a lot more. We had a lot smaller margin of error if we were willing to be only 90% confident than if we were willing to be 99% confident. So in this example, the confidence level is the probability, like 90% or 99%, that that interval contains the actual value of what we're trying to estimate, in this case, mu. So that interval is what we call the confidence interval. The confidence level was the percentage, the 99% or the 90%, and the confidence interval was that range of values, 9350 to 9950 or 9610 to 9690. Notice that the greater the confidence level, the wider the interval has to be. A 99% confidence interval is a lot wider with a lot bigger margin of error than a 90% confidence interval. So for example, if I were one of those carnival guys who guesses people, I offer to guess your age or guess your weight. And you say, okay, guess how old I am. And I say, well, your age is somewhere between 15 and 85 years old. And I'm pretty sure I'm right about that. I'm really sure I'm right. I'm very, very confident about that. Well, okay, but that's not very impressive because just saying that you're somewhere between 15 and 85 years old does not narrow it down very much. If I narrowed it down more and said, okay, you're somewhere between 30 and 34, then that's a lot more impressive, but now I'm not quite as confident that I'm right about that. I think you're somewhere between 30 and 34 years old, but I'm not as sure as I was when I said you're somewhere between 15 and 85. So the more confident you want to be, the wider the interval has to be. The other thing that affects the confidence interval is that by using a larger sample, you can gain greater precision. You can get a narrower confidence interval. You can narrow things down more. So if I just had 5 pink elephants, I would get some idea what the average weight of all pink elephants in the world would be, but not as good an idea as if I had 50 pink elephants. And if I had 500 pink elephants in my sample, then I could narrow it down even further. So here's the situation. Mu, remember that stands for the population mean. Mu is unknown. We don't know the average of some variable for some big population. And we want to estimate it from what we know about a sample. And we have a certain confidence level in mind, maybe 99%, maybe 95%, but some confidence level. And we want to find the confidence interval for that confidence level. We want to find the confidence interval that we are that sure contains mu. Like, for example, suppose we want to know what is the average weight of all pink elephants. And we take a random sample of 50 elephants, and we find that their mean weight is 9,650 pounds. And suppose we know somehow that sigma, the population standard deviation, is 110 pounds. Now, often we don't know that, but for now, assume we do. Later on, we'll talk about, okay, what if you don't know the population standard deviation? But for right now, we're assuming we do know somehow what the population standard deviation is. What is the 95% confidence interval for the true mean weight, mu, of all the pink elephants in the world? That's what we want to calculate. And here is the formula for how you calculate something like that. The formula for the confidence interval for the mean. Okay, it looks kind of complicated, but what it gives you is two numbers that you get when you calculate this formula. And it's going to tell you that mu is between those two numbers. One of the numbers is x bar minus z sub alpha over 2 times sigma over the square root of n, and the other number is x bar plus z sub alpha over 2 times sigma over the square root of n. So both parts of the formula are exactly the same, except that one has a minus and one has a plus. So in this formula, the x bar stands for the sample mean, the average weight of the pink elephants in your sample. The sigma stands for the population standard deviation. The n stands for the sample size, how many pink elephants there are in your sample. And the z sub alpha over 2 is a number that depends on what confidence level you want. So for example, if you wanted a 95% confidence interval, the number you would put into the formula for z sub alpha over 2 is 1.96. Now that's all you really have to know to use the formula, but let me explain that z part a little more. If we're doing a 95% confidence interval, that's based on that standard normal curve, and the 95% represents the middle 95% of the area under the curve. So then the question is, what z-scores would separate that middle 95% from the other 5%, the 2.5% down here and the 2.5% up here? So that little symbol alpha, that stands for the area outside the middle 95%, which would be 5% in this case. And alpha over 2, alpha divided by 2, is how much of it is in each one of those tails. So in this example, it would be 2.5%. So that's why that whole thing, z sub alpha over 2, is just the symbol for the z-score that separates the middle 95% from the 2.5% in each of those tails. Now you can work out for yourself what those z-scores are by using table E and the methods we talked about back in chapter 6. For the middle 95% and then the 2.5% in each tail, it turns out that the z-scores are negative 1.96 and positive 1.96. So you can work that out for yourself, or you can just trust me on that. So alpha is the area in the tails. Alpha over 2 is the area in each one separately. And then z sub alpha over 2 is the z-score separating that tail from the rest. Okay, that's the background. I'm going to stop there for this video, and then in the next video, we'll actually work through this example and see how that calculation actually works. It's really not that bad. It's just a matter of plugging a bunch of things into the calculator and having it give you the answer. So I'll show you how that works. We'll work through the examples in the next part, the next video.